This ever-growing trend of AI tools, a lot of developers might get caught up in deeper and deeper levels of hidden implementation detail and not trying to bother themselves how their code even work, or even the concepts behind them. My name is Oguchi Boeze from Binvevent Technologies, and in this two-part video series, I'll be explaining what your code does under the hood. Programming languages and new technological trends have made us lose grip on the actual behavior of a computer. In this video, I'll try to realign you with the concepts on which your code work. First, what is a CPU? A CPU is where the instructions sent to the computer are processed. The CPU is a part of a computer that is saddled with the responsibility of processing our code. Though ideally it can only understand binary signals which are on or off, it encompasses a vast level of implementation detail that enables it to process virtually any computable task. This part physically is a circuit built with certain ideas and concepts that enables computational logic. It exists as a single chip in most computers. Let us take a closer look at this part of a computer. This is a breadboard computer which I built a replica of back in 2018. It is a breadboard computer originally built by Ben Ita. You can check out his channel to see how this is built from scratch. I'll leave a link to his channel in the description of this video. Building this computer helped me understand the underlying principles of a CPU, which I'll explain in this video. I'll be using the parts here to explain in this video. Most are actual parts of a CPU, while some are just functional parts. Let's see how these work. Here is a structural overview of the arrangement of parts that I will be explaining in this video. We'll get to understand each part and its functions. The CPU clock. This is basically an electronic signal represented by a blinking LED, going on and off many times within a second. The activity of this clock determines how fast the commands are executed in the CPU and contributes largely to the processor speed. Clock cycle is measured in pulse per second, or hertz. 4 GHz is equal to 4 billion pulses per second, and this number can rise up to 10 GHz in modern CPUs. Here we have the RAM and the memory address register. Whether you're talking about virtual addressing or caching or memory mapping, these concepts all refers directly to the functionality of the RAM. The RAM here is a temporary storage device where data and instructions are stored while the CPU is processing data. We refer to it as a random access memory because of the multiple read and writes done by the CPU while executing instructions. The RAM is structured as an array of blocks divided into 8 or 16 segments, each representing a bit. Depending on the length of these segments, contains the amount of information read from each block. All programs is being loaded into the RAM at runtime and is executed byte by byte from the program entry address to the end of the program. Next, we have registers. Registers are also temporary storage, but these hold data that is being used in operation and needs to be read directly. A register is basically a single 8, 16, 32 or 64-bit device that can hold data in a CPU. We have various registers in a CPU for different functionalities, like the program counter which counts through the data in the RAM. We'll see this next. The instruction register which holds the current instruction to be executed. The memory address register which holds the current RAM address to be read. The memory buffer register which holds the current data read from the RAM. The accumulator or sum register which holds the result from the arithmetic or logic unit. The status register that holds data on the state of the CPU's activities. There are still various registers specialized for various activities. I won't talk about them in this video as they don't seem relevant to the topic that we are talking about today. Next is the program counter. This is a binary count circuit that counts through the contents of the RAM from start to finish. It functions by being able to count through all the addresses of the RAM and enable the contents to be read line by line, and initiates jumps and branches when necessary. The program counter is also a register. the arithmetic and logic unit. The ALU, which means arithmetic and logic unit, as the name implies, is a part of the CPU saddled with the responsibility of evaluating arithmetic and logical operations, like addition, subtraction, equal to, shift left and right, logical AND, or, NOT, and XOR. These calculations, which are already pre-built into the ALU, can be easily triggered by instructions from the control logic. It also keeps record of overflowing numbers, the zero status using the status or flag register. The control unit. The CPU has simple instructions such as load A register, increment program counter, store register A into RAM, set memory address register, jump to memory address, branch to memory address, etc. These instructions can be represented as binary data and can be used to control other CPU modules, prompting them to read data from the bus, output data to the bus, increment, add, subtract, etc. And just by prompting parts of the CPU to do certain things, it can execute these instructions. The control unit can trigger various registers to output data or read data, or ask the program counter to count up. Given these instructions, the computer can step through micro instructions to solve them. Let us take the load A instruction for instance. The load A instruction is represented by binary number 0001, and the CPU will cycle through the following micro instructions in order to successfully load the A register. Program counter out, memory address register in, prompting the program counter to put out this content on the bus, and the memory address register to read the data on the bus. This is represented by opcode 000. The RAM out instruction register in, prompting the RAM to put out its content on the bus and the instruction register to read the data on the bus. This is represented by opcode 001. The program counter increment, prompting the program counter to count up. This is represented by opcode 010. Instruction register out, memory address register in, prompting the instruction register to put out its content on the bus and the memory address register to read the data on the bus. This is represented by opcode 001. RAM out, A register in, prompting the RAM to put out its content on the bus and the A register to read the data on the bus. This is represented by opcode 100. For the CPU to successfully do a load A instruction, it's going to pass through the micro instructions step by step. Finally, let us take a look at the bus. This is the central area through which data is sent across the CPU. It serves as a channel through which data is transferred throughout the system. This ensures communication among the different modules of the CPU. Having explained the parts of the CPU, let us look at a sample assembly code to demonstrate how information can be processed in a CPU. This simple assembly code is expected to add the value of two variables and display the sum. Variable 1 has a value of 2 and is stored in memory address 10. Variable 2 has a value of 5 and is stored in memory address 12. The following instructions are given. Load A, value of memory address 10. Load B, value of memory address 12. Add registers A and B and store the results in A register. Output data in A register and halt the program. This gets loaded into the RAM and is executed as follows. Program counter out, memory address register in. Data on that RAM address is visible. RAM out, instruction register in. Current instruction becomes visible to the control unit. It prompts the instruction register to put out its address on the bus and the memory address register to read the content of the bus. The data on that RAM address is now visible. The RAM put out its content and A register reads in. While this is done, the program counter counts up. The cycle is same for the load B. Program counter out, memory address register in. Data on that RAM address is visible. RAM out, instruction register in. The current instruction becomes visible to the control unit. It prompts the instruction register to put out its address on the bus and the memory address register to read the contents of the bus. The data on that RAM address is now visible. The RAM put out its contents and the B register reads it in. While this is done, the program counter also counts up. To add, the program counter puts out its contents on the bus. The memory address register reads in. Data on that RAM address is now visible. The RAM outputs its data on the bus. Instruction register reads it in. The current instruction becomes visible to the control unit. It prompts the ALU to sum up the data on the A and B register and store its value in register A. While this is done, the program counter counts up. To put out the data, the program counter puts out its content on the bus. The memory address register reads it in. Data on that RAM address is now visible. The RAM outputs its data on the bus. Instruction register reads it in. The current instruction becomes visible to the control unit. It prompts the register A to put out its content on the bus and the I/O register to read it in. The decode logic in the I/O register decodes the content and makes the sum visible to the user. Finally, to end the program, we execute a halt instruction. Program counter puts out its content on the bus. The memory address register reads it in. Data on the RAM address is now visible. RAM outputs data on the bus. Instruction register reads it in. The current instruction becomes visible to the control unit. The instruction says to halt the program, so code is done and registers are reset. This is how a simple add instruction is executed in our computer. In the second part of this video series, we'll see an actual C programming code and try to run it using this same computational logic. Thank you.